All right, so we said, it's not up there. Valence electrons determine reactivity. Okay? And we said, who are the valence electrons? We said the valence electrons are the ones in the outermost shell. If I was in a chemistry class, what mode or method would I use or model would I use to demonstrate the valence electrons? What do they use? They use the method. They use the Lewis dot. Anybody ever seen the Lewis dot? Yeah. Okay? And if you ever look at those, they use the symbol, and then just around the symbol they use what? The valence electrons. Okay? All right. So we're talking about which ones are reactive and which ones are not reactive. All right, it says atoms with fewer than that max number of electrons in its outer shell, it says we call those reactive. Man, we don't have a thingamajigger in here. Okay, so if they have fewer than the max number of electrons, we consider them to be reactive. So if it was hydrogen, remember we know that hydrogen is reactive. What did y'all remember? What does hydrogen have? How many protons? How many neutrons? 0. How many electrons? 1. Okay, can he hold 8 in that shell? No. It only has 1 shell. We know that shell can only hold 8, but he's still what? Reactive. This one will hold 8. It's still what? Reactive. Because it's not complete. All right. Which ones are non-reactive? You should already know. Who are they? The ones with full outer shell. And somebody said something over here. The noble gases. Absolutely. That neon that you see people driving around on their cars. That is a noble gas. And it has the max number of electrons in its outer shell. The outer shell is full. This guy's conceited. Okay? I love myself. I don't need you or nobody else. Okay? So they staring in the mirror going, dadgummit, I'm it. You're it. We're it. You know? Because they don't need anybody else. They're happy all by themselves. So they're not seeking to what? To be complete, because they're already what? Complete. They're getting on your nerves because they think they all that. You know what I'm saying? But anyway, so we said the group 8, noble gases. If you're looking in your table, it's the one to the far left. Okay? So it's the one way over yonder. Far left. So every last one of those guys, complete outer shells. We ready? All righty. All right, so what can these atoms, do with their electrons? It says they can give them away, so they can give them up. They can accept them. It says, or they can do what? Share. In order that the 2 atoms or more than 2 atoms are complete. Okay? So it says that they can share electrons in order to have 8 in the outer shell. We said when you have 8 in the outer shell, what do we say that you're following? Some kind of rule. The octet rule. The octet rule. So again, we said atoms can do what with their electrons? They can give them up. We said that they can accept them, or they can share their electrons in order to have 8. Okay? Whoa. All right. So we said there's 3 common types of chemical bonds. What are the 3? Covalent, ionic, hydrogen. Good. So we said covalent bonds, ionic bonds, and hydrogen bonds. One of the biggest things that I want you to remember about hydrogen bonds. Anybody know anything about hydrogen bonds? Huh? They're what? Easily broken. Okay, unless we got a lot of them. What else? Forces of attraction between who? Okay, between hydrogen and somebody else though. But I like that the fact that he knows that they're forces of attraction. Biggest thing I want you to remember about hydrogen bonds is that they're not between just an atom and another atom, okay? They are between molecules. The biggest thing that you can remember, a hydrogen bond occurs between molecules, okay? These other bonds, the covalent bonds, the ionic bonds, they're going to occur between atoms. But those hydrogen bonds are going to occur between molecules, okay? And it's going to involve, as he said, what was your name, sir? Shelby. He said there are forces of attraction that are occurring between molecules that involve who? Hydrogen, okay? Can't have a hydrogen bond without who? All right, so let's look at the little covalent bond. Covalent bonds, we know that we are sharing a pair of electrons. So we're sharing a pair of electrons. And what happens is the electrons are able to basically orbit about both nuclei. So if we look at hydrogen gas, for example, hydrogen gas is H2, just like oxygen gas would be what? O2, okay? Now, in H2, we know that the number of protons, same thing we drew over there, was number of protons is 1, number of electrons is what? 1. We know the number of neutrons is what? 0, because there aren't any. The mass was what? 1, correct. All right. So if we drew this guy, we just draw the 1 proton, or we could just put P in the nucleus. We know that he has 1 electron. A minute ago, you told me that he was unhappy. And he needs what in order to complete his outer shell? He needs 1 more. So he can bind with another hydrogen and share their valence electrons. And these valence electrons can orbit about both nuclei so that they're both satisfied. So they are sharing this pair of electrons. So they're sharing a pair of electrons. So 1 and 1 makes 2. All right, so it says in covalent bonds, electron pairs are shared between the outer shells of the 2 atoms. And then that's hydrogen gas. Of course, I couldn't get my little circles close enough, but anyway. So we're sharing a pair of electrons. And we said that those electrons are able to orbit about both nuclei. We ready? No? Okay. Just yell at me when you are. Okay. All right. So, again, we said that they form hydrogen gas. We said each atom is now, having this full outer shell. Again, because we said the electrons are orbiting about both nuclei. So it says hydrogen gas can also be represented by the symbol and stick model. So meaning that this bar in between the two represents a what? Covalent bond. So that's just not a line, okay? It's actually what? Representing the covalent bond. So this solid line that's in between the two symbols represents the covalent bond. We said the covalent bond is a very strong bond, okay? And when you break that bond, you release energy, okay? So anytime we break bonds, we said we release some energy. Anytime we make a bond, we're storing energy within that bond that's been created. All right, I'm coming around the room. You can pick a piece of candy. Just put your hand in the bag, whatever you get is yours. Will it work? Okay. Go. Will it live? Okay. I'll try to bring Jolly Ranchers next time. This is chocolate today. Mm-mm. That's too bouncy for me. All right. Now, come on now, Cletus. Been here all day. You're welcome. Sorry. You're welcome. All right, the rest of y'all gonna have to wait because I gotta go back up to the front. Class will be over by the time I'll get y'all next week. Just kidding. All right. I'm going back to the front. All right, here we go. You ain't getting none. All right, oxygen gas. We said it's a slightly different bond. Now, what I want you to do, I want you to draw the Bohr model, one Bohr model for oxygen gas. But be thinking, because this is going to create a slightly different one, I want you to draw the Bohr model for oxygen gas, but give me a double covalent bond. Try not to look in your book for that. I mean, you don't have to close it, but, try not to peek-a-poo. Draw it out. You're welcome. You're welcome. There you go. Sorry. You're welcome. You're welcome. You're welcome. Oxygen. I want you to do oxygen gas, so that means you got to at least draw one, but be thinking because it's a double covalent bond that you've got to place your electrons in the right place, because in a double covalent bond, how many pairs of electrons do we actually have to share? 2. So that means we got to have 4 electrons kind of in the right position. So you want to start one. Did you get some? Okay. All right. Mm-hmm. Ladies, you're welcome. Sneak through. Gentlemen, you're welcome. I don't. Anybody got a couple sheets of paper you could borrow? Thank you. Did I miss y'all? Why do I know you? Shouldn't I know you? Yeah, I know, yeah. Did everybody get it done? Not yet. You're working on it? Should be drawing oxygen gas. So that means 2 oxygens. Mm-hmm. All right, guys. Right. You got to put your other,
2 more?
yeah, on there. Mm-hmm. Uh-huh. Except for you got too much going on in the middle.
What do you mean?
You only need to share 2. Like this one. Like that should have been flipped like this. Like flip this whole one over there. You know what I'm saying? You see what look at his. But it'll work. Yes. Yes. Perfect. Yes, it's going to be when you finish the other one. Look. Okay, here we go. You can't leave any off just because you're thinking it's going to, right. Because, look, how many do they have in the outer shell of the oxygens? 6. How many do they need?
8.
So how many do they need? 2. So each has what? 6, but he's going to share 2 with the other one, right? This one has 6, but he's going to share 2 of the 6 with the other one. Does that make sense? So they're actually sharing the 2 pair of electrons. But anyway, what do we have in the nucleus? 8 protons, 8 neutrons. First shell has what? 2 electrons. Next shell has what? 6. So we got 1, 2, 3, 4, 5, and 6. The next one. And one of the things that you probably notice is that in covalent bonding, the shells or the clouds actually overlap, okay? Because they have overlapping clouds, and we can draw them as overlapping rings. So 8p, 8n. First shell still had the 2. The next shell, 1, 2, 3, 4, 5, and 6. So they're going to share 2 pair of electrons. So even though they're able to orbit about, he needs what? 8, and he needs who? 8. So that's correct. Cool beans? Okay? Because they're sharing 2 pair of their electrons in order to complete the outer shell. So that was the one. And then there's the second one. And again, we said that they're sharing 2 pairs of electrons. All right, so if we were to look at it, we would draw the symbols, the 2 symbols for oxygen. And then we want to put 2 bars in between because we said it's a double covalent bond. It's a double covalent bond. And know that there's a possibility of having a triple covalent bond, but I won't make you draw that today. Okay? Any questions so far? All right. And I'm not going to make you draw that, but anyway. How many pair of electrons are shared here?
3.
How many pairs of electrons? 1 pair.
3. 1.
How many electrons?
1.
How many electrons? How many electrons?
6. Oh, 6.
Thank you. Did everybody get that? How many electrons are here? 2 electrons. 1 from hydrogen, 1 from who? Carbon. How many electrons are here? 6. 2 from each carbon. Okay? 1 from each carbon, but you've got, 3 from each carbon, excuse me. Okay? So in other words, what we're looking at, if we just looked at carbon alone, one of the carbons, we would have 6 P, I think 6 N's. I'm guessing, but I think that's correct. We'd have 2 electrons in the first shell. The last shell would have, I believe, 4, correct? All right, so we would have 1, 2, 3, and a 4. And we would have that 1 proton, not P1, that 1 proton. But anyway, make sense? So that's the one end of that guy, okay? And then we could just flip that around and do another one the same way and get the other side of. So this is acetylene gas. If anybody that used torches and that kind of thing. All right, that won't be on your test, though. All right, covalent bonds. It says everything that we've done up until this point was what we would consider to be a non-polar covalent bond. What do I mean by non-polar? Good. So electrons, protons, whole nine. So in other words, what we mean by non-polar is the fact that no atom within this covalent bond has a stronger pull on the electrons. Okay? So it says because they're identical, they even have an identical pull on the electrons. Because when we say something is polar, it means that one of the atoms that's within the bond has a stronger pull on the electrons, and if he has a stronger pull or draw on the electrons, then his end of the molecule is going to change in charge. He's going to carry a partial charge of some sort. If he takes it all the way, then we want to call him completely polar, and he will be more of an ion. Okay, so we want to say nonpolar covalent bonds have the same pull on the electrons. And we said polar covalent bonds, we said that in a polar covalent bond, someone has a stronger pull or draw on the electrons, okay? So covalent, nonpolar, covalent, we say everybody has the same pull or draw on the electrons. So a hydrogen gas, is that nonpolar or polar? Nonpolar. They're the same. Atom H1 and H2. They're identical. Yes, they have the same draw or pull on the electrons because their nucleus is identical. Okay? Same draw or pull on the electrons. So it says, well, how do we set up a polar covalent bond? How would we set one up? It says, well, where somebody has a small ionization potential. If somebody has a small ionization potential, it says that they have a willingness to give up or let that electron be drawn away from them. Okay? If my electron is being pulled away from me and it's closer to somebody else, what does that do for me charge-wise? Right. So that means I'm going to have a partial. Now, if I give it up totally, I'm going to have a total charge of positive. But if it's just being drawn away, because if we're talking about covalent bonds, what are we doing with the electrons? Sharing them. So nobody's losing the electron, but it may be drawn away from me so that it's further away from me. But that's going to give me a partial positive charge. So my end of the molecule is going to be partially charged positive. So if I'm the end that's actually drawing that electron closer to me, then my end is going to be what? More negative. So it's partially negative. It would be totally negative if I do what? Steal it or take it, right? All right. So we said that's a positive end. It says if I have a large value for the electron affinity, to automatically tells you if I'm loving the electrons and I'm pulling them towards me, then my end is going to be the end that's going to be more negative, and my end is going to be the end that's going to draw that electron towards it. So then that leads us into talking about another guy, and his name is Linus Pauling. Okay? And Linus Pauling says that each atom has an ability to attract electrons, and the ability to attract is called electronegativity. Okay, so the ability to attract an electron is called electronegativity. Depending on if you were in a chemistry class, they would put the electronegativity values in your chart. Okay, but we don't necessarily need the electronegativity values, but we can learn the trends for electronegativity values. So in other words, as we move towards the left side, over there where oxygen is, over there where fluorine is, over there where nitrogen is, that side is going to be more electronegative than this right side over here where hydrogen is, where sodium is, where potassium is. Okay? So all these guys over here, we have a tendency to give up our electrons, and they be lost to the other side, or they be drawn further to the guys on the other side if we're actually in a bond with those guys. Okay? Are we done with this slide? Nope. Then y'all need to start printing some slides and bringing them to class. Are we, is this making sense so far though? Okay, good. Somebody said no. Ability to when I say ionize, again talking about either losing or gaining an electron. In that instance, we lose, because we're becoming positive. Yeah. All right, ready? Uh-oh. Going one way and not the other. All right. Here we go. It says, if we move from bottom left to upper right, it says we're going to increase in electronegativity. If we go down the table, we're going to decrease. So in other words, we're at the top of the table, we're moving down, we're going to decrease. It says if you're moving across the table, so in other words, if we're going from this side over to that side, we're definitely going to increase in electronegativity. If you just remember anything that's over yonder, the oxygens, the nitrogens, but we know who's not included. Because remember, what was that last row called? Noble gases. They're not included in this. So it's before we get to the noble gases, okay? So we know that those guys over there are going to have a stronger pull on the electrons versus the guys that are going to be over here. Mm-hmm. Mm-hmm. Okay, and it's doing its own thing.
This is a partial chart of that they have in the book.
That is correct. It just went off. Hello. 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 All right. Now, hopefully that was the next slide. I want to make sure. Oh, come on. Is that the next one? Okay, just making sure. All right. So let's look at water. It's a polar molecule where we have one oxygen that's bound to two hydrogens. And we know that the nucleus of the oxygen is bigger and more positive than the nucleus of the hydrogen. All right, so anyway, let's go with oxygen. These lines, of course, represent what? Good, covalent bonds. All right, it says, according to that, which we're missing a couple things off of there, but we know that who's going to be the most electronegative within this bond? The oxygen, correct. So the oxygen is going to draw the electron, not take, but draw the electron closer to the oxygen. And he's also going to do the same thing for that one. So that's going to set up polarity on this molecule because now the oxygen is partially charged to negative and the hydrogens are partially charged how? Positive. So now we have a polar molecule because we have one end of the molecule that is now what? Negative or partially negative. We have one end of the molecule that's partially positive. Yeah. All right, so what we want to say then is, what, if I ask you a question, what made water a polar molecule, how could you describe that to me? Because what? I can't. Say who? Okay, is it because oxygen has a negative charge? There we go. Got to put that in front, okay? So we want to use that word electronegative, okay? So you want to tell me that because oxygen is what? More electronegative than the hydrogens, it has a stronger pull or draw on the electrons.
And what makes it more electronegative? The fact that it has more electrons?
Yeah, that's one of the reasons. Correct. 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 No. Right, so it has a higher, because oxygen has or carries a higher electronegativity value than hydrogen. That immediately lets us know that oxygen has a stronger pull or draw on hydrogen's electrons. And because of that, it makes the oxygen partially negative and the hydrogen partially positive. Okay? So we know that electrons are spending more time around the oxygen than they are around the hydrogens. So it's not that they're not there, they're just spending the more the cloud is drawn towards the oxygens. Okay, so don't forget that definition. You will see it again, and you will lose points if you don't know it. All right. What time is it? 1:30. We got 15 minutes. We're going to do ionic bonds, and we'll be done. All right, so it says, when electrons electrons are transferred. So we're talking about a complete transfer. From one atom to another, we form ionic bonds. We're talking about the complete transfer of an atom's electrons from one atom to another. The complete transfer of one atom's electrons to another. So we call those what? What words did we use a long time ago? Maybe last class period. What word did we use? We call them what? When they lose an electron or gain an electron, what do we call? Ions. And then what two kinds did we have? Cations and anions. Good. Cations were charged which way? Positive. And anions are charged? Good. All right. Here are our rules. It says ionic bonds are going to form between strong electron donors and strong electron acceptors. So strong electron donors are those that have one or two electrons in their outer shell or in their valence shell. So a donor has one or two in its outer shell. So that would make this guy that's still on the board a what? What is he? A donor. Good. Strong electron donor. Because potassium only had what? One electron in his outer shell. So it's easier to do what? Give away one than it is to take who? 7. Just lose it. Bam! Kick it out the door. Hey, that's what he said too, didn't he? He said, you know, when you're ready for success, you got your act together, you're going to do what? You're going to, bam, put your foot up, bam, kick yourself through the door. Hey, I'm ready. I want everybody in here to make, hey, I'm telling you, I'm going to be mad at y'all for real. Because I'm sick and I'm at school, I'm still giving it my 120. I go to school at night, I don't get out of class at 9:45 p.m. So when I leave here, I go to class. Class starts at 5:30. We get out at 9:45 p.m. I'm tired. I got a headache. I got science problems. But I want y'all to make an A. So I got to give y'all 100 like I feel great. And I don't. And I'm fat, too. You know, that don't help either. You know, Dr. Oz said, you got belly fat, you're going to die. So I need to be doing something about that. But anyway. You know, because seriously, visceral fat is some of the worst fat that you can have. Visceral. You know, it leads to all kinds of extra hormones that lead to all kinds of extra things. You know, leads to cancers. Okay? Visceral. This stuff, what I got plenty of. Mercy, Lord. But candy is good. Real good. Huh? Okay, I'm telling you, I got to do better. But anyway, but the one dude, he won't let us eat in class. Then the next dude that shows up, he brings everybody a Coke, you know. But I can't drink them. But anyway, I'm a diabetic. All right, so y'all don't bring me candy. But if y'all ever see me eating any candy out this bag, hit me. Not real hard though, because it might hurt. Like tap me on the hand. Pow! You know better than that. All right, here we go. All right, so strong electron acceptors are who? Atoms with 6 or 7 electrons in their outer shells. So they're going to take, it's easier to take just that one. Boom, I got you. Or that two. Boom, boom, you know. But it's kind of hard to throw all those guys, you know, get them our way. Okay, so now we know. So this is our general rule. We said 1 or 2 in the outer shell. And this happens only when what? When hydrogen was with hydrogen, did he give it away? No, because they equally shared. But when we put hydrogen in the presence of a strong electron acceptor, then he's going to do what? Give it away, okay? So in other words, like if we were looking at hydrochloric acid, for example, you know, bam, I'm going to give that away. All right, here we go. So NaCl, let's look at NaCl. And usually most of these are salts that we're talking about. All right, here we go. NaCl. We said this is a good example. What is NaCl? Sodium chloride, and it's also where we find it. On your table, right? You're going to put it in your food to enhance the flavor. All right, so the first thing that I want you to do is to draw sodium and put its stats down. Hurry, we got to hurry up. Sodium is Na, right? If you don't have your book, what is it, 20? Thank y'all. So if you can draw sodium and then chlorine beside it. Put your stats out to the edges. Sodium, chlorine. Put your stats out to the edges. What's wrong?
Is that right?
Yep. No. What's that one? Oh, yeah. No. Yeah. I'm sorry.
It's okay.
I told you I had a headache, right? I'm on my last leg. I have not anything left right now. Hey, did I pass the roll? My goodness. Let me get it going. It's coming. Okay, y'all sign and pass. Sign and pass. Yep. I went on and rounded it up. Yeah, you're good. She can go boom, boom. Okay, now, let me tell you. I don't want you to draw these overlapping. Overlapping was who? Covalent. They need to be separate. Okay? So maybe the second week in September we'll be ready for a test on that Thursday. Just skip that day. Y'all got it? Okay. 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 Yeah. Well, what's that? Is that a 19? Okay, you finna fix it. Okay, great. Okay, what's wrong with this picture? Okay, that's right. 23 minus 11, leave what? Thank you. Right. Okay, I'm counting. Okay. Yes, sir. Okay, this is just sodium. Now you got to draw chlorine. Yeah, so that's right. That's sodium. That's fine. That is fine. All right. So everybody got sodium and chlorine drawn? I said I want them side by side, didn't I? But I'll take that. It's all right. I know you don't pay attention well. It's all right. Yes, sir, Chris. We ain't got that far yet. Hold on there. Hold on. Hold on. Hold on. Let me get mine drawn right quick. All right. So we said, okay, how many people have been online and seen that there are videos in your box? Integrity videos? So like today's lecture will be in there. Bohr model, how to draw a Bohr model was in there. So today, how to do this stuff, and then there'll be an extra video on how to do covalent bonding. There'll be an extra video on how to do ionic bonding. So you guys got practice at home. So I'm there too if you pull me up. All right. Okay, sodium. Somebody help me real quick. We got 11 protons, 12 neutrons. We got 2 electrons in the first shell, 8, and then just 1, right? So we're going to put that 1. Then we got, what's the other one? Chlorine. 17 protons, 18 neutrons, right? First shell is going to have 2. How many? No. 8, and then who? 7. 1, 2, 3, 4, 5, 6, 7. We said that this guy is going to do what? He's the what? He's the donor. This guy's the... Okay, don't forget your labels. This is going to be very important for the test. You also want to put on here sodium. You also want to put on this one who? Chlorine. Good. All right. So then we want to say that since we know that he's donating, we're going to draw an arrow because he's getting ready to give that up. This one you always have to draw twice. So if this is worth 10 points, you're going to get 5 points for the first time you draw it. Okay? You need to draw it again because this guy, when he donates an electron, he actually loses this outer shell. So that means you have to draw it again without the outer shell, and you have to draw it again with this one having how many now? 8. Good. So we're going to redraw this guy a second time with our 11 protons, 12 neutrons. I don't know what this is for, but it's in, oh, it came down, okay. Okay. So 2. And then this guy just has what? 8. Yeah, because we didn't lose them. We only lost electrons. Okay? So then this becomes what? Somebody tell me, what is his charge? Good. So he becomes Na plus now. And then the chlorine, he was 17 protons, 18 neutrons. First shell, 2. Next shell, 8. Last shell, 8. Okay? And he becomes what? Cl minus. Good. So now we want to call this one a what? Cat ion. And I want to call this one a what? An ion. Then I'm going to ask you, how is that bond held in place? You going to tell me what? What y'all gonna tell me? What'd you say? Okay, and that did what? Okay, how? Okay, and more. Some. Boo. Okay. Boo. All right, tell me, what do these do? That's it. That's all. Positives and negatives. So the positively charged atom attracts the who? The negatively, and the negatively attracts the who? Positive. So it's simply the attraction between the negatively and positively charged atoms or ions that hold it together. Boom. That's it.
Wait, what does that look like?
My question was, yeah, what holds the bond in place?
Attraction.
Boom. That's it.
So wait, so it's not like the other one where, like, actually nothing's overlapping or touching. It's like
Right.
next to each other.
Correct. All righty. Thank y'all very much. Have everybody sign the roll sheet. Where is it? All right. Would you ask me?